Looking at matrix induction in this video. So usually matrix induction involves repeatedly multiplying matrices, like many powers of them. So first thing we should do is revise matrix multiplication, because to be honest, that is the bit that can be tricky about this if you haven't done it in a while. So just as a little refresher, to multiply matrices like this, you would go 3 times 1, and then 2 times 2 in the result. So it's that row with that column. And then here you would have to go 3 times 8, and then 2 times 5. For the next column, 6, 4, and 1, 2. So that is 6 times 1 plus 4 times 2. And then you're going to go 6 times 8 plus 4 times 5. Once you get all that in, you can actually just work out what these numbers are. So this first one, for example, will just be 3 plus 4, so that's 7. Next one's going to be 34. Next one here would be 6 plus 8, so that's 14. And then next one here would be 6 times 8, so that's 48 plus 20, so 68. Just like that. Now, the way you actually know whether you can multiply matrices is you just look at the dimensions of the matrices. So these are both 2 times 2. The middle number matches, which means that you can, and the resulting matrix that you get is a 2 by 2. Now, usually in induction, we are going to be timesing 2 by 2 matrices, but just for example, this is how you would do other ones. So this is a 1 by 2, and it's a 2 by 1. So the middle number matches, which means we can multiply the matrices, and we're going to get a 1 by 1 matrix. So we're actually going to get a single number here. That number is going to be 1 times 3 plus 2 times 4, which is just the number 11. Beautiful. Now, if you wanted to do matrices like this one here, you actually can't, because this one is a 2 by 4, and this one is a 2 by 4. So can't do. And the reason we can't do that is because 4 and 2, the middle numbers, don't match each other. Anyway, with that out of the way, we're going to do our induction question on matrices. I'm also going to show you how to make a conjecture. So this matrix here, I've actually got in the calculator already. But to enter that, you would go matrix there, and you would enter it like so. But now that we've got that set up in the calculator, to use it in calculator mode, you go Shift Matrix A, and then it just pops out like that. And then we can start looking at some higher powers of A to see if we can spot a pattern. So we'll immediately see A squared is going to be 2 with minus 2, and 2, just like that. A cubed, you might be spotting a pattern already potentially. Shift matrix A cubed, 4 with minus 4 with 4. Now you can do this for as long as you want. I might do one more just to make sure that we can spot the pattern. So A to the power of 4. My guess is that it's going to be this, but we will check on the calculator. So let's do that. Matrix A to the power of 4 is that. So what are these numbers doing? Well, when you're making a conjecture, what you probably want to say is they're doubling each time. That's something called a recursive statement because you need the previous answer to get the next one. What we would like is an answer which gives us any power of A. So in theory, I should be able to calculate A to the power of 8, for example, which, fun fact, would be 128 minus 128, etc., etc. How did I know that? I know that because these are all powers of 2. So really importantly, these ones here. So all these numbers are 2 to the 1, all these numbers are 2 squared, all these numbers are 2 cubed. You'll notice that the power of 2 is 1 less than whatever the matrix power is. So we can actually make a conjecture. So conjecture, A to the n is always 2 to the n take 1. For all n in Z plus. So there's our conjecture. Now let's prove it using induction. Okay, so P1. Now technically when we make a conjecture like this, we've actually already done the base case, but let's just check it. So A to the 1 should be, well, That's just the matrix A, which is the original matrix we started with. And then you can almost think about this as your left-hand side. On your right-hand side, we're going to get 2 to the 1 take 1 for all of our powers. Which is going to give you 2 to the 0 for each spot. And 2 to the 0 is just 1. So we're done. 1 minus 1 minus 1, 1. So therefore P1 is true. So PK is our next step. So we're going to assume that A to the K is 2 to the K minus 2 to the K. These should all have take 1s on them. Minus 2 to the K take 1 and 2 to the K take 1. I just moved that one so it doesn't look like it's the same expression. We'll call that star, and then we're going to say for some K in Z plus, as we tend to do with inductions. All right, now we're going to move on to proving PK plus 1. So in particular, the matrix A to the K plus 1, we're going to split it up much like a lot of other induction methods. A to the K we already know, so this is the matrix 2 to the K take 1. And then we're going to be timesing it by the original matrix A. Now let's think about what our want to show should look like before I move on here. You can do your want to show at any point, but I like to do it near the start. For our want to show, we would like to show that A to the K plus 1 is 2 to the power of K plus 1 take 1. So again, that is just the statement here, except instead of having K's, I'm having K plus 1s. That's literally the only difference. Every time you want to do a want to show, that's exactly what you do. All right, so this next one should be minus 2 to the K plus 1 take 1, minus 2 to the K plus 1 take 1, and 2 to the K plus 1 take 1. And then that is just going to be 2 to the K minus 2 to the K minus 2 to the K and 2 to the K. So that's what we'd like to show. Wonderful. Okay, so let's actually do this matrix multiplication. And you'll notice we actually have to do the multiplication by hand. There is no cheesing this on your calculator. You got to just do it. So let's see what we get. We're going to get 2 to the K take 1 times by 1. And then minus 2 to the K take 1 times by minus 1. That's our first term. Next one we're going to be doing is this one here. So we're going to get minus 1 times 2 to the K take 1. And then take 2 to the K take 1 times by 1. Next term, we're going to do the bottom row to get that. So we're going to be doing minus 2 to the K take 1 times 1, and then plus 2 to the K take 1 times minus 1. And then for our last term there, we're going to have minus 2 to the K take 1 times by minus 1, and then 2 to the K take 1 times by 1. Now this looks pretty awful, except it is going to simplify down nicely. So you might notice here, this first term here, this one and this one are actually just the same term, because in that last term, both negatives cancel out and make it into a positive. So this is 2 times 2 to the K take 1. This next term is negative can come out the front, 2 times 2 to the K take 1. And then it sort of just works like that. So it's collecting like terms. And then this last one should be 2 times 2 to the K take 1. You can do a middle step here if you want as well. You could have, like, for example, this one here being 2 to the K take 1 plus 2 to the K take 1. And that would show you that it is 2 times 2 to the K take 1. Now we just use index laws. So if we have a situation like this, we add the powers. So we're left with 2 to the 1 plus K take 1, 2 to the K. And I think we've done it. And then all we do is finish it off by writing this statement that we normally write at the end. Be aware that in exams, sometimes you get a follow-up question asking maybe about specific powers of A and asking you to compute those. So it's worth practicing follow-up questions like that.